Chapter 20, Part 3. All right, we're going to talk about the reactivity of carboxylic acid derivatives and then get into some groups of reactions. I will warn you, there's a lot of reactions coming up in the rest of this chapter, so we want to stay organized. We're going to look at the different classes of compounds here. The acid halides, the anhydrides, esters, and amides. We will finish up with nitriles at the end. And this is the ordering from most reactive to least. The acid halides and anhydrides make really good synthetic starting materials. Esters and amides react in much the same way, but they're much less reactive, they're more stable, and so you find them in nature more frequently. We're going to look at some of the reasons for this reactivity. So looking at induction and resonance, it's easy to see why our reagents are reactive, right, for a nucleophilic substitution. So the carbonyl, we already know this carbon is electrophilic. We saw that with aldehydes and ketones, but it's even more so because instead of carbon and hydrogen on both sides, we've got some Z group, either a halogen, oxygen, or nitrogen, which is also going to be more electronegative than carbon. You also see, because the Z group will have lone pairs, you'll see an actual resonance structure that gives that full positive charge to that carbonyl. This is less true for the nitrogen, for the amide, because a nitrogen is less electronegative than chlorine and oxygen, and so that pull right here is going to be less. It's still going to behave very similarly, it's just not going to be as reactive. The next thing that we can see when we talk about the reactivity is how does Z act as a leaving group? Because in many of the reactions that we're going to look at here, we are going to be replacing Z with some sort of nucleophile. So that means that Z will have to survive on its own. We saw this in Organic 1 when we looked at substitution reactions. We know that halides make great leaving groups because they're the conjugate bases of strong acids. I'm going to come back to that slide in just a minute. This is a good leaving group because it will be resonance stabilized. OR and NH2 are much less stable. We know that an alkoxide and an amide are actually fairly strong bases, and so they're not as stable when they leave, right? Which contributes to them not being as reactive. They still, however, can leave as opposed to an R group or a hydrogen. That's why aldehydes and ketones have their own chapter, right? All the carbonyls aren't in one chapter because they have very different reactivity. We never saw an aldehyde or a ketone losing a C or an H. So when you go to approach problems in this unit, it's really important that you start off looking at this substrate and decide what category does it fall in. Aldehyde and ketone or carboxylic acid and derivatives. Leads to very different products, even though sometimes it might have similar reagents. We are going to look at a lot of specific mechanisms, and something you're going to notice repeating within those mechanisms will be a nucleophilic attack and loss of leaving group. What is important to recognize, this is 2 steps. This is not an SN2 mechanism. It's not concerted. Your nucleophile attacks in 1 step, leaving group leaves in a 2nd step. This is not an sp3 carbon, so it just behaves differently than the substitutions you learned on alkanes or alkyl halides. You are always going to open up that pi bond and make a tetrahedral intermediate. I will say this and then an abnormal amount of times. All right, and then it will close back in on itself. And if you have something that works as a good leaving group, the leaving group will leave. There's going to be a lot of specific examples. This is alcoholysis, which we will cover as we move forward into specific reactions. All right, just reiterating, not a concerted process. I want to stop here for a moment. We get this reminder periodically. If a reaction is under acidic conditions, then you are not going to produce strong bases. You are not going to use strong bases. If we have basic conditions, we are not going to produce strong acids. We are not going to have positive charges. It's important that you pay attention to what is actually present in a reaction. If you need to move a proton around, which you're going to have to do frequently, you want to make sure that you are using something that's actually there. And we'll reiterate this as we learn actual reactions. We will see hydrolysis also occurring. We'll talk about this one specifically in a moment. The reason that it's here is to point out the acid catalyst. Some of our reactions require an acid catalyst. Some do not. It's a catalyst, so it catalyzes the reaction by affecting the activation energy. You can read through that on your own. I'm going to keep going because we will look at that specific mechanism when we get to that reaction. Not all of our reactions have to be acid catalyzed. Sometimes we have a strong enough nucleophile or a strong enough electrophile, right? In this case, it depends. It just depends on the combination that you have. So it's important to pay attention to what reagents are being used, right? Stay organized. Okay, well, we know proton transfers will come and go. So we're going to keep going. We are going to go ahead and I am going to skip over this specific hydrolysis mechanism. It may seem like I am skipping a lot of slides, but it's because they're very repetitive. They are going to come up again after we do the preparation of acid chlorides. So you can read through them, but no, I'm not skipping anything that I'm not going to talk about coming up. So we're going to jump in with acid chlorides, right? These are our most reactive. Acid bromides would work in a similar fashion, but I'm only going to show you how to prepare an acid chloride. So that's going to be the focus of this section. An acid chloride is our most reactive, and so it is really nice to know how to make this, especially when you get into multi-step synthesis. And a carboxylic acid is not going to have the same kind of reactivity, especially because you have that acidic proton. So if you want to do something like a Grignard, it's not possible on this guy because of that acidic proton. So you have to doctor it first. And you can do that with thionyl chloride, SOCl2. That is going to replace the OH with a chlorine. You do not need to know this mechanism, though it is interesting. If you like unique mechanisms, you see this one on 2 pages here. All I need for you to know is how to predict the product, and you need to know this reagent. This will come in handy throughout the rest of the chapter. Because if you can get to a carboxylic acid, you can get to an acid halide, that will open up the door for synthesis. That is the only preparation reaction that you need for acid halides. We are going to look at 3 big types of reactions: hydrolysis, alcoholysis, and ammonolysis, that have a lot of key features that are very similar. We're also going to see all of these reactions for several of our functional groups. So you may be responsible for a mechanism for each functional group, but I may only walk through it one time. So this is our first bit of organization. There's a lot of reactions, but if we can start grouping them together, it can be helpful. Okay, so starting with hydrolysis. We are taking an acid chloride and we are reacting it with water. Now, something that you are going to note, hopefully here, again and again, you are removing the Z group and the hydrogen of the nucleophile. And then everything outside the box kind of smushes together. So we wind up with a carboxylic acid. If you notice, there is no acid catalyst here. And that's interesting, right? Because water is not considered a strong nucleophile. We needed an acid catalyst when we had aldehydes and ketones. But there's something special about that acid chloride. It's really reactive, right? It's way more electrophilic, so you actually don't need the acid. The water will attack this highly reactive carbonyl all by itself, right? So if we go into the mechanism, and we'll just go down and around for the mechanism, once I have that nucleophilic attack, I'm going to make my tetrahedral intermediate. It's okay to make that negative charge, especially if we didn't have an acid catalyst. So it's a neutral solution here. All right, and we have the chloride. Now, the chlorine is such a good leaving group that when this folds back down, you could certainly get water to pop off, but the chlorine is actually going to be a really great leaving group. And so we'll lose that chloride. In one final step, we just need to deprotonate that hydrogen here, or I'm sorry, this protonated carboxylic acid to get to our final product. Now, you don't have hydroxide around. You don't have a strong base. You could show the chloride, but we know that's a very weak base. So when in doubt, water can work as your acid or your base. And in this case, it's going to be your base, and it's going to deprotonate. So we have a nucleophilic attack, followed by a loss of leaving group, followed by a proton transfer. This is the first of many of this type of reaction. So you want to make sure that you're going to get lots of good practice showing these mechanisms. Occasionally, you will see pyridine tossed in the mix. And while pyridine is basic, it's really just there to absorb the protons that are lost in this reaction to neutralize any HCl that shows up in the reaction. If you see PY, that's just letting you know there's pyridinium. There's pyridine there. You don't have to. You don't have to. I'm not going to require that you always write that down, but that's what it is there for if, in fact, you see it. Alcoholysis is going to look very similar. All right, we're going to have our acid halide. We are going to react it with an alcohol. There might be pyridine around to absorb that acid that we're going to make. And we're going to make an ester. Right, so this gives us access to esters. If very much the same mechanism, we're going to attack that very electrophilic carbonyl carbon. We don't need any sort of catalyst here because, again, our starting material is so reactive. We make our tetrahedral intermediate. We still have that proton on the alcohol, so don't forget that. And we have a good leaving group. Our carbonyl reforms and we lose chloride. And then all we're left to do is deprotonate so that we have our neutral product. You could show pyridine coming in, or you could show the alcohol here acting as your base. As long as it's something that's present, you're good. Something that you guys have to pay attention to is what functional groups are reacting. We have an acid, chloride, and an alcohol. It really doesn't matter which one is on the arrow and which one is off to the right. I mean the left. It's going to be an alcohol and an acid halide giving you an ester. The reason this might be on the arrow, it has to do with what are you interested in? Did this take you a long time to make and this came from a bottle? Well, then you might put this one on the arrow, right? The point being that it's these two functional groups that react together. There is going to be some preference for less sterically hindered alcohols, but I'm not going to ask you to do anything like this, so don't worry. Ammonolysis works exactly the same way. Ammonolysis, we're going to take our acid chloride and we are going to react it with either an ammonia, a primary amine, or a secondary amine. What's important here is that there is one hydrogen. We are going to still lose HCl, and we are going to wind up making an amide. Whether there's 0, 1, or 2 R groups, it's going to follow the same mechanism. Your amine is going to attack. You are going to get a tetrahedral intermediate. The tetrahedral intermediate will fold in on itself and kick out the chlorine. You will have your protonated amide. And there's no reason to bring in pyridine. That's why there's two equivalents here. The amine itself is a base, and it can neutralize that acid. It can act as a base all by itself. So you'll often see two equivalents here. That's all that means. It doesn't add twice. It's just there. One equivalent to add or to substitute, the second equivalent to pick up protons. All right, so we have a bunch of different reactions here between hydrolysis, alcoholysis, and ammonolysis. You're going to be responsible for all of these mechanisms, but it's really not that bad so far.